Hi, Calculus 3 students. So this, I believe, is part 5. Yeah, it's part 5 of my series of lectures on power series. Okay, so at this point, we have seen a couple of power series, and we have seen a case in which it converges for some values of x and diverges for some other values of x, but we also saw that for some values of x, um, the ratio or the root test were inconclusive. Now, the first thing I want to tell you before going any further is that if you, let's say, apply the root test and it's inconclusive, don't apply the ratio test. It will be inconclusive as well. The theoretical framework for both tests are really, really similar. So when one of the limit is going to give 1, the other limit is also going to give 1. So that's the first thing. So it means that sometimes for very specific values of x, we will need to resort to another convergence test. And I like to brag about it a little bit. I wrote them all on the board. I was able to fit all other tests on a single home whiteboard. Can you imagine? And now let's review them a little bit together, because these are the tests that you will apply on these specific values of x. So first of all, the test for divergence. If you find out that the limit of the general term is not equal to 0, then in this case, the series diverges. Okay, so you have to be careful because this doesn't go the other way around. Like if you find that the limit of the general term is equal to 0, it doesn't mean that the series converge. So this is a quick test to apply, but it is very, very often inconclusive. So you have to be careful about that. So the test for divergence is like if the limit is not obviously 0, try it. And if it doesn't give 0, you know right away that it's divergent. And if it gives you 0, you have to do another test. But at least you didn't lose a lot of time. Most of the time, these limits are pretty quick to evaluate. Okay. Then the integral test. Okay, the integral test. By the way, there's two things to keep in mind when you apply these tests. One of them is in which case can you apply them? So with this one, you can apply this in any case. Like you just take the limit. If it's not 0, it diverges, regardless of the series. But here you have some conditions. Let's underline these conditions. I'll do it in blue. Okay? So what conditions do you need in order to be able to apply what's called the integral test? You need a function to be positive, continuous, decreasing, that matches the general term when you feed it integers. Okay, whenever you plug integers in the function, it must give you the general term of the series. And if that is all satisfied, the series converge if and only if the integral converges as well. I want to tell you that you apply this test as a last resort most of the time when none of the other tests are working out. And the reason for that is because when you apply this test, you need to make sure / prove that your function is positive, continuous, decreasing. And you have also an improper integral to evaluate. So that's not always easy, and sometimes it's not even possible. So keep that in mind when you apply this test. P-series. Now, P-series are an application of the integral test. If your series looks like this, okay? So this is a condition, right? In the sense your series must be a P-series in order to apply this. It will converge when the exponent here is greater than 1, and it will diverge if the exponent is less or equal to 1. Okay, so again, when can you apply this? Only in this specific scenario. So if you look at the conclusion, it's very powerful. It's going to tell you exactly when it converges or when it diverges. But the problem is that it works only for very, very specific cases. After that, you have the alternating series test. So the alternating series test works for only one kind of series, and it's called the alternating series. It's whenever they alternate in sign, right? All the terms, they alternate in sign. You get like plus, minus, plus, minus, plus, minus, Or it could start with a minus. You don't care. As long as you have this sequence of plus minus, plus minus, plus minus, you can apply the alternating series test. And what does it says? Like, first of all, this Bn greater than 0 just says disregard the sign when you apply this test. Okay, you know that it's going to alternate. Okay, disregard it. If you take the limit of the rest and it's giving you 0, and if Bn plus 1 is smaller than Bn, so the term with larger n's are always smaller than the terms with smaller n on some interval from n to infinity. So it doesn't have to start right away, but past some value of n, uh, like it must decrease monotonic. Oh my gosh. Okay, well, it must, all these terms must be smaller than these terms, like always. Like the subsequent terms will always be smaller than the previous term. Okay, then in this case, the series converges. Now, what I have to say about the alternating series test is be very careful about the implications. So it's an if-then type of statement, right? If this is satisfied, then the series converge. If this is not satisfied, then we cannot say anything. Well, if the limit is not 0, by the test for divergence, you know that the series diverges. Okay, so that's one good thing. But if the limit is 0 and this is not verified, the series could be convergent or divergent. So this is really an if-then type of statement. If this is verified, you know that the series converge, but otherwise, you cannot say anything. Let's now go at the direct comparison test. Okay, so when does it work? It works when you have two series that you can compare with each other that have positive terms. Okay, this is really, really important. You cannot apply this if the series sometimes have positive terms, sometimes has negative terms. You cannot. And if this is true, then what it says basically is that if an is smaller than bn and the bn series converges, then the an series converges. Like uh, since this series is finite, has a sum, this also has to be finite. If an is larger than bn and the series of bn diverges, which means like it doesn't have a sum, the sum is like approaching infinity, then in this case it will be the same for the series with larger terms. Okay, so it will be pushed to infinity by the series with bn. Okay, but keep in mind this is only applicable if you know that all the terms or all the terms past some values of n at least are all positive. Okay, finally, you have the limit comparison test. By the way, in some book, the word direct will not be here. It will be just written comparison test. But I like to say direct just to put some emphasis on the theorem's little sister, the limit comparison test. Same hypothesis, right? You need positive terms to apply that thing. And now you make a limit out of it. Okay, so you make the limit of an over bn. So you're comparing these an and bn by putting them in a limit and dividing them. So if the limit is finite and not 0, okay, so here, if c is finite and non-zero, then you have this conclusion. It both converge or both diverges. Okay. If c is equal to 0, so if you take the limit and c is 0, it means that bn dominates an, right? So what it means essentially is that if the series with bn converges, the series with an must also converge. Like the limit will not be equal to 0 if this is finite but this is infinite. Makes sense? If c is infinity, so in other words, if the limit that you have here gives you an infinite limit, then it means that an dominates bn. So in that case, if bn diverges, if this is approaching infinity, it's impossible for this to converge. It has to also go to infinity as well. So there you go. If the series of bn diverges, the sum of an also diverges. So in the next video, we're going to finish the example of the previous video, and we're going to figure out if the series that we saw before is converging or diverging at these values of x equals -7 and x equals 3. See you there!